So, hello. Let's start. Today we are going to proceed with qualification procedures and testing. And in the last session we have seen about reliability data, for instance, we have seen fit numbers. And today we are going to deal with how to get such data. That is very important. So testing is one of the key elements. On the other hand, it is important to know that testing needs certain strategies. So we must learn in which phase of product development, for instance, we have to perform which tests and what the test strategy will be. Okay, let's proceed. Let us regard a more complex system. So, for instance, it would be a sensor system, and that is a sensor system which is sold to an end user. And normally, the question is now, how do we get a dependable product which fulfills all of its quality criteria? And the first thing is we must define a specification, and that specification is derived in a top-down way. So normally, for instance, you would have a sensor system, for instance, for your household. The question is, what requirement do you have as a customer? In a company, such information must be gathered by different sources. For instance, there is some customer service, also the development department, and so on. And now imagine such a complete system has different parts. For instance, there is one microsystem in it which gives us, let's say, for example, which has a gas analysis microsystem. Again, that system must be specified, and that specification is derived from the system's specification. So it is necessary to derive such specifications top-down, and imagine such a microsystem would consist of hardware, software, assembly, and packaging. And for each of these, we must specify something. For instance, for the hardware, we must specify what kind of computer it is. Is it 16-bit? Is it a 32-bit? For the software, is it real-time? Is it not real-time? And so on. The packaging, how good must the protection be? And so on. And what is important, if we derive a specification from a higher specification level, that lower specification must be validated. Validation is a formal process where we look whether the lower level specification can be fulfilled if we set the higher level specification as, let's say, as the boundaries within which we have to specify. And in that way, specifications are derived top-down. For instance, in the end, we come to the material specifications, so we know the housing is made of metal in order to make it hermetic, and so on. And only when the specification is complete and when the specifications on all levels have been validated, then we can start to design the system Here in the previous branch, we have more a concept than a design. So here we design it and we build it bottom up. So we get the material, we do materials testing. That's, for instance, also very important when we produce implants. Yeah, the materials must be biocompatible, for instance. The materials must fulfill certain requirements, also according to some laws or standards. And again, the testing relates to the specification, and then we go to the next level. Here we build the hardware, we program the software, and so on. And here we have so-called verification. Verification is a check. What is the difference between validation and verification? To say it a little sloppy, a validation is a formal process. After the formal process, you get some approval that it is okay, and verification is also a validation, but on the other hand, it comprises experimental parts. So here it is in detail the testing which is important. And finally, the complete microsystem is integrated, and after the final integration, we do the testing. That is in the development and generation of such a system. But we must see, normally in a company, we do not have a single product which has a single development, but a company has many products, it has many microsystems, and so there can be a more efficient approach to this. First of all, let's come back to the specification. A specification must be correct. So you cannot specify something which is wrong, and also it must be complete. So there are requirements, the customer has requirements, the authorities have requirements, and that's the reason why a specification must be complete. Yeah? You cannot forget something. When some years ago I did some consulting for a very big and top company which produced diamond tools for cutting concrete. So these are huge machines, and it is more or less an electrical motor and a blade, and that diamond blade cuts through concrete. So if you need a door in that concrete wall, you can cut a hole in. Okay, that company decided to go from electromechanical system to electronically controlled system. So they had electronics designed, and that design and production of the electronics was produced by another top company in the field of power electronics. In the end, they assembled it all, sold it to the customer, and a few months later, all of the customers came and say, "Oh, our machinery is broken, it doesn't work anymore." And in the end, what was the result, or what was the cause of these failures? The company had forgotten to specify vibration as an important property. So you can imagine if such a diamond blade cuts through concrete at high speed, there are huge vibrations. Of course, it's extremely loud there, and those vibrations, maybe 10G or 20G, act on the electronics, and so the power electronics virtually fell apart. That was a very impressive example, what happens if you forget something in a specification. So it must be complete. On the other hand, it must be free of contradiction. So that can easily happen, that you require two things. For instance, you specify a car that has a speed of 300 kilometers per hour and consumes only 2 liters per 100 kilometers or so. Yeah, that would be evident contradiction, and such contradictions must be found. So what is also important is that a specification must be capable to be verified and validated. Yeah, if you specify something where you cannot find out whether it is valid or not, then it will not help you. So let's say the proof of validity is a formal procedure, and it is called validation. And that is important, and that is always the starting point of development. In Germany, there is a distinction where we have 2 steps. The first step is more like a specification. That's the so-called Lastenheft. That means that is the properties which have to be fulfilled. And on the other hand, we have the so-called Pflichtenheft. That is a description how to fulfill these requirements. Okay. Now let's get over this. We already mentioned that in such systems, you could say it's a mechatronic system or it is an embedded system. So what does it comprise? It comprises some hardware, for instance, some sensors. It comprises some software, and also we have the assembly, packaging, and the external parts. And typically, these 3 parts are developed in a different way. So if we look at the hardware, where we would say here it's more the mechanical parts, like a motor or so, you could say this hardware part is more, let's say, the duty of the mechanical engineers. Software is, of course, something for computer science people, and assembly and packaging is a special branch for people building electronic systems. So what is important is the following, that these 3 branches are not only different part of mechatronic or embedded systems, but it is also 3 different worlds. So you have the world of mechanical engineering. Here you have processes like machining. You have special software like CATIA, for instance, and certain finite element software for mechanics, or also for electromagnetics. On the other hand, the software people, they do not have a tool shop. They work in an office. They use computer tools. And the assembly and packaging people still have another tool set. So they use, for instance, layout software for printed wiring board or several things. And in each of the branches, the developer goes for analysis, design. Testability is always an important part. So testability in mechanical parts means, for instance, also measuring size, what are mechanical tolerances, and so. And in the end, it is tested. Hardware is tested, software is tested, reliability is tested. What is very important when you have the hardware and the software in mechatronic systems or electronic embedded systems, It is important that hardware and software is tested all together. Yeah. The reason is that hardware is often designed in a way that it is, let's say, not over-designed. It is just fulfilling duties, but that could also mean that, for instance, to check whether real-time requirements are always fulfilled with a certain hardware. So if the, let me say it blunt, if the computer is too slow, yeah, you can have problems with with real time. Okay, so these three parts of such a system, or let's say an anti-brake locking system, are developed by different people, even in different companies, and in the end the system is put together and it must be tested as a system. Yeah, okay, so here we can see a system is quite complex, such as embedded systems or a mechatronic system, a mechanical electrical system has several levels top down, and on the other hand it also has several let's say pillars on which it is based, which are mechanical engineering, electrical engineering, and software. Okay, but on the other hand, now let's go to testing, and specifically for testing of electronic devices. And normally you could say, okay, I built my system and on every level I test it, and in the end I'm quite sure it will work. But on the other hand, you have to keep in mind that that the failure rates of individual devices are very complex. They are very low, and even if the system is complex, the overall probability of failure and the overall failure rate can be low. And also, as a rule, it will not help you if you test something and when you do not have any failures, because then you also will not get the information what can get wrong. And now the question is, how can I make a new technology reliable? How can I get the reliability data? And how will I get this new technology into my product? And here we have to address so-called processes. Processes are some actions which are repeated all of the time in a company for individual generations of products. And now let's have a look at the life cycle of such a product. For instance, just take an example, we would like an anti-brake locking system. I don't know why it doesn't write here. We have an anti-brake locking system, and we want to introduce a new technology, which would be a BGA, as you know, a ball grid array. And now, how can I get this BGA into my new anti-brake locking system generation? And now, first of all, we cannot just take new BGAs and build them into anti-brake locking systems. We must first investigate that new technology, and that means we build test samples, we design these, we do so-called end-of-life testing. That means we get failures. That already means how long do we have to test? Until we have failures. You cannot say we test for 1,000 hours or 3,000 hours or 1,000 cycles, but you test until you get failures. And you get sufficient failures in order to do statistics like Weibull distribution. Okay, when you have enough information and you know it is reliable enough, you can go into fabrication processes. That means now you can produce in your factory test samples, and here you can investigate how printed wiring board assembly process with BGA can be accomplished. So here we could say, for instance, BGA on printed circuit board. What will be the result if there are soldering defects and so on. So here we do a fabrication process development. And that's in our factory line. And here again we do design of experiments. We look for test methods. For instance, you could say, how can I check in production if there are defects in my samples? So you could, for instance, introduce X-ray testing and so on. And only when this has been accomplished in a successful way, you can go into product development. So you do not yet produce a product, but now it's really product. It is anti-brake locking system, for instance. You develop it, maybe you do generation 1, later on generation 2. And when you are finished with the development and you have again a qualification at the end, you get into fabrication. And then you're on the safe side. Again, you must test, for instance, during production. You have non-destructive testing like X-ray, which you have developed in the fabrication process development. So that means in the end, in that multi-step process, you get a reliable product. And you cannot just say, I develop a new anti-brake locking system and I go into fabrication without doing all of that technology development and fabrication process development. That's very important. Sometimes people drop this, for instance, because they have some contract manufacturer, so they can really go into product development, into fabrication of the product. So the company only does this and the rest is purchased, but this contract manufacturer must have these 3 capabilities. So that means the life cycle of a product is quite complex. And here you could say the complete time from definition of a new technology until you come to a product which is running in series that goes over a minimum, let's say, of 5 years, and the complete cycle until the product is outdated and is redrawn from the market, it could be 15 to 20 years. Okay, here is just a description of what I just told you. And now let's have a look at the different cycles, phases of that life cycle. So first we have the research and technology development. And here what is important, we want to have failure. We want to analyze and optimize design parameters which can affect reliability. So in order to define that, we need failures. Yeah, we also do systematic failure analysis, what can go wrong, and also what is important is we have an optimization. In the process development, it is very similar. We already know, for instance, it's BGA, but now we want to do an assembly process with BGA. And there are more parameters which come from a series production. And again, it is a systematic variation. In the end, also, we are still interested in getting failures. When we do a product development, normally we design tests which are similar to the phases 1 and 2, but how long do we test then in the product development? So here we indeed say we want to have it for a lifetime of, let's say, 3,000 cycles, and we test for 3,000 cycles or even for 4,000, and we require that there is no failure. Or maybe some say, okay, we just accept one failure or so, but in the end, you already want to be failure-free, so you meet the specification, and the specification could require a minimum lifetime. And it's similar in series production. Here you only take certain samples in order to know that all is fine. Also here you do accelerated test. You do not want to waste your money with too much testing. You just want to be sure that what you get out of series production has no crucial defects and is of standard quality, so you have no variations. You want to have a constant fabrication, both with respect to the parameters you use for the prefabrication and also for the output quality level which your product must meet. Okay. We have seen that, and now what is important is we have several phases of the product development, and in these phases we must distinguish, for instance, how long we test. Yeah, so we have seen in the initial phases where we want to do technology development, we want to see failures, we want to learn from these failures, we want to know what the influences on failure rate are, and on the other hand, excuse me, please. On the other hand, sorry. Excuse me.